In this video, I'm going to talk about Lewis electron dot diagrams. In these diagrams, you show the outer electrons, which are called valence electrons. The reason we care about these electrons is because they are the ones that are involved in all the bonding between atoms and interactions between atoms. If they form ions, these are the electrons that they lose or gain. And so it's the outer ones that we really care about. There's a direct correlation between electron configurations, and I have a separate video showing you how to do this, and Lewis electron dot diagrams. Let's say we're going to do a electron dot diagram for magnesium, which is right here in the second column of the periodic table. So magnesium has 12 electrons. If we did the electron configuration for this, it would look something like this. And those are the 12 electrons. Remember, the S and P are sublevels, and the big numbers tell you what row of the periodic table you're on. Those are called the quantum numbers. And so if we look at this, our outer electrons are not going to be the ones on the first level. They're not going to be the ones on the second level. All we care about are these that are on level 3. And we have 2 electrons on level 3. So the way that we would do the Lewis electron dot diagram for magnesium is we would put the symbol, and then we would put 2 dots. And I know that in middle school sometimes they show going around 1 dot per side, but that really only works correctly if you have 1 electron or if you have 5 or more. So it really only works for column 1, 15, 16, 17, and 18, and the whole middle part would be incorrect. So we show these 2 electrons together on one side because they are together in one sublevel. So this is where I put my S sublevel electrons. It doesn't matter what side you do it on. So Mg with 2 dots on the right is the same as Mg with 2 dots at the top, Mg with 2 dots at the left, or Mg with 2 dots below. Just be consistent where you start. And the way I do it is I always start with my S on the right, so that's how I'm going to do it in this video. Let's look at an atom that has some P electrons. Let's look at nitrogen. So we're going to have a full 1s2, then 2s2, 2p3. So nitrogen, with its 7 electrons, its electron configuration would look like this. Again, we don't care about the inner ones. They're tucked inside. We only care about the ones that are in the outer shell, which are these S and P electrons, which is a total of 5 electrons. So we would put our nitrogen symbol like that. Here's my 2 S electrons right there. And now I have 3 P electrons. Now, a P sublevel has 3 orbitals in it. So the electrons are going to spread out as far away as they can. So one will go in each of the 3 orbitals, and top, left, and bottom are what I use for my P electrons. And they spread out as much as possible. So we have a shared pair, and then we have 3 unshared, which the unshared locations is where bonds can be made, because another atom can come up here and share one of its electrons, and then they have 2 electrons here shared between them. So these open spots, because you can fit 2 electrons on each side, these open spots are where bonds can form. So just by looking at this, we can see that nitrogen can actually bond 3 other atoms. For our third example, let's do argon, 18 electrons. So the level 1 is full, level 2 is full, and level 3 is full. So argon is going to be, has 18 electrons. It is the same as the noble gas before it, neon. So here's argon. It's the same electron configuration as neon plus our third row of electrons, which is a 3s and a 3p, and both of these are full. So our 3s has 2 electrons, our 3p has 1, 2, 3, 4, 5, 6 electrons, like so. So we have a total here of 2 plus 6, or 8 electrons that we're going to put around the symbol. So argon is a noble gas. It's very unreactive, and the reason why is because it has 2 S's and 6 P's. So we spread it out. That's 3 P's, and then we double as needed. And now we have 6 P's, 2 S's, and notice all the sides are full. You only have a top, bottom, left, and right. And the most you can fit in each of these orbitals is 2 electrons. So this is full, and that's why argon is very stable. Let's look at one from the middle. Let's look at chromium. So chromium has 24 electrons, and it is the same as argon plus 4s2 3d4. Remember, the D is back 1 level from the row it's on. So our argon had 18 electrons, and then in addition to that, we have 4s2 3d4. Our symbol for chromium is Cr. Now remember, we're only going to show the outermost electrons, which means the ones on the highest, with the highest quantum number. This one quantum number is 4, this quantum number is 3, so we get to ignore those, they're tucked under, and we just have to show these 2 S electrons like that. The same thing happens if you get a giant atom with F level, sublevel electrons. Those are tucked under, and so those would not show either. So the only electrons you're ever going to show in a Lewis electron dot diagram are S and P electrons for the row that it's actually on. So knowing that makes it pretty easy, because everything in the first column is going to have 1 S electron in its outer shell. And everything in the second column is going to have 2 electrons in its outer shell. So everything in column 1 is going to look like this, with 1 electron. And everything in column 2 is going to look like this, with 2 electrons. We looked at what happened with the transition metals. The S electrons showed the D were tucked under, so we only had to show the S. So all of our transition elements, let's say we do copper, have 2 S electrons. So this is column 1, this is column 2, this is column 3 through 12. Now we get to our P block, and our S is full, before we start filling our P. So we're going to have 2 electron dots and then however many P we have. So if we're in column 13, we have 2 S's and 1 P. For example, boron, 2 S's and 1 P. And it doesn't matter where this one goes. It could have gone over here, it could have gone up there, wherever you want to put it. Just on a different side than the 2 S's, which are together. Column 14 is this column with carbon at the top. We have 2 S's and 2 P's. Now, there's an exception to this, so I'm not going to show carbon. I'll come back to that. I'm going to show germanium, Ge, as my example. So I am going to have 4 electrons. So I need to have 1, 2 together, and then 2 separate. The exception to this 2 together and spread out the rest is carbon. Carbon is special. When we do carbon, we show 1 on each side because carbon generally shares electrons, and so the electrons spread out 1 to each side and it can make 4 bonds. Column 15 has 5 outer electrons. So if we look at column 15, the top of it is nitrogen. Let's do phosphorus, which is the second one down. We're going to have 2 together, 1 on each side. Column 16 has 6 outer electrons. So if we look at column 16, let's do sulfur. Needs 6 outer electrons, 1, 2, 3, 4, 5, and now we have to double somewhere. Now, when you do this, column 16, and you double, make sure the doubled ones are adjacent to each other. Don't go like this, because that's going to make, when you start doing bond shapes, that's going to make this look linear when it's really bent. So don't write it that way. Keep these 2 adjacent to each other. Column 17 has 7 outer electrons, 2 S's, 5 P's. So if we do fluorine, 2 S's, 1, 2, 3, 4, 5 P's. Notice it will only make 1 bond. This is the only place where a bond can form, where we have an electron that's by itself. And our last column is column 18. Most of them are going to have 8 outer electrons. However, helium in our first row, remember, it's just got an S. See how it's orange? It's really a 1s2 is its electron configuration. Like these are all S2s, that's why it's a matching color. But it's a noble gas because the 2 is full for the first level, the first shell. So for helium, it will have 2 electrons. But for neon through radon, it's going to have 8 electrons. It's going to have 2 S's and 6 P's for a total of 8. So if we were to do krypton, Kr, we would put 2 S's, 1, 2, 3, 4, 5, 6 P's, and see how it's full and unreactive. So our 2 exceptions that we saw to the rest of the rules was carbon, who puts 1 electron on each side, and helium, which is a noble gas with a full shell, but remember our first shell can only hold 2 electrons, while all shells 2 through 7 can all hold 8 electrons when they're full. So all we need to do is find where an element is on the periodic table, and that will tell us how to do its electron dot diagram. So let's say you are supposed to do indium. Well, it's in column 13, so it has 3 dots, 1, 2 S's, 1 P. So indium would be IN, 2 S's, 1 P. I hope this has helped. If you have questions about other topics in chemistry, I have lots of videos linked in the description, and I hope you have a great day.